Hi, I'm Jen. In this presentation, I'm going to talk about and show measurements of power quality created by three different photovoltaic systems in Northern California. Residential PV systems use an inverter to transform direct current power generated by the solar panels into the alternating current power that most of our home appliances and fixtures use. PV inverters use pulse width modulation switching to transform power from DC to AC. This controls the magnitude and the frequency of inverter output and eliminates low order harmonics. On the other hand, it does generate high frequency harmonics. You might ask, what are high frequency harmonics? A pure sine wave or perfect electricity would look like the picture on the left. Every wave is the same. This is purely theoretical. In practice, perfect sine waves don't exist in electricity. Dirty power might look like the picture on the right. Waves are erratic in form and timing, and they vary. Let's make a baseball analogy. Perfect electricity is like batting balls from a pitching machine. The balls get pitched in the same way to the same place with the same timing every time. It's easy to get into a rhythm. Dirty power is like batting balls pitched by a team of little leaguers. You just never know what's coming next or when. High frequency voltage transients, harmonics, dirty power, and dirty electricity are all different ways of saying the same thing. The process of transforming current from DC to AC always creates dirty power. Dirty power includes voltage spikes, dips, surges, harmonic distortion, and electromagnetic interference. It can cause equipment malfunction, reduced lifespan of electronics, flickering lights, potential safety and health hazard, and it wastes energy. This is especially problematic as we move towards all electric homes, which are filled with delicate electronic equipment that can be easily damaged. Something else to consider. Our power grid is aging, and we risk destabilizing it with low quality power. As we move towards a distributed power generation system in which individual homeowners become their own micro power plant and feed power back to the grid from their personal solar systems, we need to be thinking about the cumulative effect that this may have on the quality of power that's then redistributed by the power companies. Solar inverters, like other electronics, are subject to electromagnetic compatibility testing. This is called EMC testing for short. Manufacturers are required to show that the inverters are not affected by electromagnetic noise and other interruptions. This is known as immunity testing. And also that the inverters create minimal noise themselves. This is known as emissions testing. The testing that I'll share in this presentation, harmonics testing, is the sort of homebrewed type of EMC emissions testing. The IEEE 1547 standard regulates how distributed energy resources, such as solar power and batteries, can connect to the grid. As usual, California is leading the way. We mandate certification of inverter safety and power quality with the most recent IEEE 1547.1-2020 conformance specification. Hawaii also mandates the 2020 specification. A few other states have adopted the 2018 version, which does not regulate harmonics. Most states are still using the 2003 version, which is incredibly outdated at this point. We need all states to get on board with the 2020 version. However, even the 2020 version doesn't go far enough. We should be mandating that inverters generate higher quality power. We should be requiring the addition of enough cheap, customized filters within the inverters to clean up power to a higher standard in order to protect the grid, the electrical devices that are connected to it, and the people who use those devices. In this presentation, I'll show that different inverters create different varying levels of power quality. Sometimes a simple external capacitive filter can help clean up the harmonics. Sometimes a more customized filter would be needed. I'll show these harmonics using screen captures generated by a consumer-grade oscilloscope. The testing equipment I use is a Picoscope 2204A oscilloscope, a Stetzer ubiquitous filter that removes the 60 Hz signal, a Mixig DP1007 high voltage differential probe, a Hantek HT201 20:1 attenuator, a Hantek HT-30A BNC to banana adapter cable, and a Stetzer capacitive filter. I measured three systems, a 19.2 kilowatt PV system with a Sol-ark 15K inverter with a separate EG4 PowerPro wall-mount all-weather lithium battery, a 4.3 kilowatt PV system with a standalone ABB inverter, and a 6.2 kilowatt PV system with SolarEdge HD-Wave String Inverter with solar optimizers for each panel, and two 15K Tesla PowerWalls. All of these systems are in the Northern California Sierra foothills. You may have seen an oscilloscope trace before, but before I show you the data, let me explain how I have it configured and what you'll be looking at. I'm measuring two things. The frequency domain on the top shows the different frequencies that are present and in what amounts. My measurements will show frequencies from 0 to 50 kilohertz. The time domain on the bottom shows how the signal changes over time. The blue and red traces represent two different views of the electrical signal. The blue trace shows the entire signal, including the 60 hertz signal. It's here to provide an anchor point in where we are over time. If you enlarge the blue trace, as on the left, you'll see that it's slightly jagged. The fuzzy parts are the harmonics that are magnified in the red trace. The 60 hertz signal has been removed from the red trace so we can see the harmonics better. The x-axis in the time domain goes from minus 20 to 20 milliseconds and shows the interval of power. The y-axis in the time domain shows the voltage. The range for the blue signal on the left goes from minus 160 volts to 160 volts and represents the entire signal. You might be scratching your head and asking, why 160 volts when our voltage in the United States is 110? Good question. The oscilloscope range is up to around 40 volts. To get these measurements, we scale it with a filter in front by times 20, and then the software rescales it back. The scale must have been slightly off. I don't personally think this matters much for this presentation because the value of this exercise is to look at the visuals of the harmonics. If we were in a certification lab, of course, we'd need more exact data. In this slide, the range for the red signal on the right goes from minus 2 to 2 volts and represents just the harmonics. Unfortunately, the inverters are so different that I wasn't able to use the same scale for all measurements, but I'll point that out as we go. I measured all the systems at the closest outlet to the inverter. All other circuits were off. The circuit for that outlet had to be on, but nothing else was running on that circuit. I measure the inverter and battery by just turning on those circuits. For each system I measured, I'll show the baseline coming from the power company first. Then I'll show the signal with the inverter running and another with just the battery, if there is one. Halfway through each measurement, I add a Stetzer capacitive filter. Sometimes this is enough to clean up the signal, and sometimes it's not. In all cases, a custom internal filter that's designed for the device itself would work better than my generic capacitive filter. Okay, now I'll stop explaining so we can finally look at some data. The first system I'm showing is a Sol-ark system. Here we're seeing the PG&E baseline that's coming in for that house. As a reminder, here are the system specs. 19.2 kilowatt PV system with a Sol-ark 15K inverter with a separate EG4 battery. This is a lot of solar panels because it powers two all-electric homes with car chargers and a number of outbuildings. This home only shares a power pole with one other home, which is somewhat distant and does not have solar. The first slide shows the baseline of power coming in from the PG&E pole. The signal is pretty clean. The filter didn't really change it. Now I'm showing the Sol-ark inverter. There are a lot of harmonics here. The filter cleaned it up slightly, but it didn't help too much. For this system, the scale on the bottom right y-axis goes from minus 4 to 4 volts. This system was fairly dirty, and I needed this range to be able to visualize the harmonics. The blue-gray within the red signal is actually an artifact of the video compression. It doesn't mean anything. Now I'm turning on the EG PowerPro battery. There are even more harmonics than with just the inverter. You can see when I add the filter, but again, it doesn't make much of a difference. Now we'll move on to our next system. This is a SolarEdge inverter. This is a 4.13 kilowatt PV system with a standalone SolarEdge inverter and no battery. For this system, the scale on the bottom right y-axis goes from minus 2 to 2 volts. Even so, the baseline power coming in from Roseville Electric is fairly dirty to begin with. The filter does clean it up. This system is in a smart tract home neighborhood where all of the neighboring homes also have solar. Perhaps this is why it's dirtier power. It's hard to say. Now I'm measuring this ABB inverter. It's not very different from the baseline, but again, all the neighboring homes have the same system. The filter does clean it up. And finally, we're moving on to the last system. Here are the system specs. This is a 6.2 kilowatt PV system with SolarEdge microinverters and 2 connected 15K Tesla PowerWalls. In this system, it's not possible to decouple the inverters and battery wall. This home is on acreage and shares power pole with one other home. It's unclear whether the other home has solar or not. For this system, the scale on the bottom right y-axis also goes from -2 to 2 volts. The baseline signal here is fairly dirty. Adding a filter does clean it up. I don't think that I measured the Tesla Powerwalls in this measurement. I took this measurement later in the day when the batteries would have been full, but the sun was still shining, so the system would not have been pulling from the batteries yet. I would like to measure this at some point during the day to see if I get a different measurement for the Tesla Powerwalls. Finally, here are all three systems together so we can compare them visually. The middle system and the system on the right are both probably measuring similar inverters, so it makes sense that they are similar. As a reminder, the scales are different, so the system on the left is twice as bad as it appears compared to the other two. In summary, here are the takeaways from my talk. High-frequency voltage transients can be measured with consumer-grade equipment. Harmonics created by solar inverters vary. And finally, we need better standards to protect our power grid, our electronics, and our occupants. Thank you for listening.